All right, so we'll get back into the material that we left off last time. So we're doing applications of these exponential models. And now that we know how to solve exponential equations or solve logarithmic equations, we can use those in word problems. Most of the problems I give are exponential equation type problems because every log problem can be rewritten as exponential and vice versa. So here we go. So just as a reminder, the formulas that we're going to use, if we have compounding interest m times per year, then we use this formula. If we have compounding interest continually, then we use this formula, P e to the RT. Our doubling time formula is this one, P times 2 raised to the T over D power, where D is the time period it takes to double. And we have a half time formula as well, where we just put the half in there instead of the 2. Okay. And if you wanted to do a tripling time formula, you can put a 3 in there instead of a 2, or a quadrupling, put a 4 instead of a 2. But usually the more common ones are half times and double times, right? And so we did that with example 1, and then also with example 2. I'll remind you, example 2 was done in hours, so all of our time in hours. And we ended up with a formula that said the amount of bacteria, we started with 1,000, and we knew that the amount doubles every 1.5 hours. So we ended up with this equation. I guess I don't need to do that. And then we used that equation. We plugged in T a couple of times, a couple different values for T, and then we plugged in a value for A and then solved it, right? So we had an exponential equation. Plugging in values for T is just evaluating the exponential. And then plugging in values for A and finding the T, that was solving the exponential equation. Okay. So that's what we did last time, and that was the one we ended up. Okay. So let's do another example of that scenario with a percentage rate, in this case, decay. So it says a city has a population of 45,600 in 1995. Since then, the population has approximately decayed continually at a rate of 0.8%. Create an equation for the population of the city after 1995 using T as the number of years since 1995. So that means T of 0 will represent 1995, T of 1 represents 1996, and so on. Okay, so we will create a model. Where T is years since 1995. Now, after we do that, we'll ask some follow-up questions. We'll say, if this rate continues, what will the population be in 2035. And then it says, in what year will the population reach 40,000, or did the population reach 40,000? And then how long until the population gets cut in half, gets halved? So if we are either growing or decaying continually should give you a heads up that we're using P times e to the RT. Okay. P is my initial amount. Well, since we're using 1995 as our starting year, my initial amount is 45,000. My initial population is 45,600. Now, here's the thing to watch out for. A decay rate, we went over this way back in the beginning, but a decay rate is a negative R value. And if it's 0.8%, then that means the R value is negative 0.008, just under 1%. Does that make sense? So R value is negative 0.008, and then we had T. So that would be the equation that we want. If it asks for an equation in Moodle, make sure that if you type in E caret, you might need parentheses around the exponent so that all of that stuff goes into the exponent, right? If you typed it in as E caret negative 0.008 times T, then it might think that you want to calculate this. Does that make sense? So be careful about that. Again, Moodle will interpret what it thinks you mean, and if it doesn't look like the thing you think it means that you want to write, play around with it, make sure it gets in there correct. Now, the population in 2035, that 2035 is 40 years beyond 1995. Just subtract 2035 minus 1995 gives you 40 years. And so if I'm looking for the population in 2035, I just plug in a 40 for my T. And if I round to 2 decimal places, I get 33,112.40. That's rounded to 2 decimal places. Since this is population, it might ask you to round it to the nearest whole number. But on the other hand, this is also a projection, so it doesn't we know those projections always don't turn out to be nice whole numbers. So the population in 2035 would be about 33,112 people. Fair at that. Get the same thing I did. By the way, it is a decay. We went from 45,600 to 33,112. So we went down. That's a good sign that we're at least on the right track. We're on the decay track anyways. So there you go. Now, how long until we have 40,000 people? We're going to take 40,000 as the amount of people we have after a certain time and figure out what that time would be. So we take 40,000, set it equal to 45,600 times e to the negative 0.008 t. And then solve that equation. So I divide both sides by 45,600. That's not going to divide real nicely, but that's okay. Not a problem. Take 40,000 divided by 45,600. That's equal to e to the negative 0.008 t. And now apply natural log to both sides. Since I have base e, I'll apply natural log to both sides. So natural log of that ugly fraction is equal to, when I take natural log of the right-hand side, I just get negative 0.008 times t. So we have coefficient of negative 0.008, and we'll just divide both sides by that coefficient. Divide by negative 0.008. Be careful when you type this in. For this fraction of 40,000 over 45,600 is in the argument of the natural log, but the negative 0.008 is not. Okay. You can do that in one step on your calculator or two steps, doesn't really matter. When I did that, I got approximately 16.38 as my value of t. Now, last step here. If it asks me for how long it takes until it reaches, for the population reached 40,000, we'd say, well, after 16.38 years, but that 16.38 years is 16.38 beyond the year 1995. Okay. In Moodle, they may ask you for the number of years beyond 1995. It also could ask you for the actual year, too. And if we want the actual year, all you do is take your 1995 and add that 16.38. That is 2011.38. So sometime right during the year 2011. Okay. The population is 40,000. So not at the beginning, but you know. Does that make sense? I'm not sure which one Moodle will ask. Depending on the question, it could ask you for the number of years after 1995, or it could ask you for the actual calendar year. All right. So if it asks you for the calendar year, it's talking about 2011. Now, with the last question, how long until the population either was halved or is halved or will be halved? We don't know if it's yet, if it'll be past today's date or before today's date. So how long until the population gets cut in half? Well, there's a couple of different ways to do this. We have this formula. That's the equation. So one option, if the population gets cut in half, I can just figure out what half of 45,600 is. So 45,600, divide that by 2, that's 22,800. So one option is to take 22,800 as my end value. And then solve it in the same way we did over here. Now, in this circumstance, when I divide both sides by 45,600, on the left, I get a half. And on the right, I get e to the negative 0.008 times t. By the way, this kind of leads me to my second option. My second option is realizing that was always going to happen no matter what I started with. Here I started with 45,600. This was half of that. If I would have started with 10 people, then I would have gotten an A of 5. And in this step, I would have ended up with a half. We follow that? So another option is just to think of this last amount as half of your principal. And realize that when you divide both sides by whatever your principal is, you get a half equals t to the negative 0.008 times t. So whatever our principal started with, time it takes to get a half can be calculated by just taking the amount to be half the principal, divide by the principal on both sides, and you get that. So I didn't have to really do the work of figuring out the amount, the half amount of 45,600 is 22,800. I could have just skipped that step because I knew I was gonna get this. That makes sense? And then either option from here is the exact same solving. I apply natural log to both sides. Natural log of a half is equal to negative 0.008 times t. And then divide both sides by negative 0.008. Again, make sure that the 1/2 is inside the argument, but the negative 0.008 is not. When I did that, I ended up with 86.64. And that means the population will get cut in half 86.64 years beyond 1995. What is that? Add 1995 to that. 2081.64. 2081. So sometime in the year 2081, the population will be half of what the 1995 population was. Is that right? So again, you can, if you want to, use actual numbers, or you can just realize that if we're taking half of what we started with, once we divide both sides by that number, we're going to get half. Okay. We'll use that principle a little bit later too. Okay. I want you to try this one on your own. This is again decay continually at a rate of 1.15% per day. So you got to do everything in terms of days. T will be in days. And so what's the half-life? And then if a doctor injected 60 milligrams, how much would be left after 50 days? Yeah, try this one on your own. All right, so let me go through this as I walk around. I kind of looked over some shoulders and doing all right for the most part, but there's a couple of things. First off, if I'm setting up this equation, initially, it doesn't tell me how much I start with. Iodine 125, that's just the name. So, like, that's the isotope number. Okay. How many neutrons, electrons, protons, that kind of stuff. So, that's just the isotope. Doesn't tell me how much of it we have. So, it's still just the variable P, basically. So this is our initial setup, okay? It doesn't actually ask you for that. This question doesn't ask you to write this, but this is what's happening, right? Initially, I don't know, but I do know we're decaying at a rate of 1.15%. That's negative 0.0115 as a R value. So if it says find the half-life, doesn't matter how much I start with. Whatever I start with, the half-life is how long it takes till my starting amount gets cut in half. Does that make sense? Whatever my starting amount is, it'll get cut in half. and that would be my ending amount. So I'm solving this equation. Some people just use the number 1 for P because that's just easier. You can use whatever number you want, including a variable P, like I did. Apply natural log to both sides. That gives you natural log of 1/2 is equal to the exponent of negative 0.0115 times t. Then I would divide both sides by the coefficient. So half-life is the time it takes for your initial amount to be cut in half. Okay, so that's the big thing. Half-life is the time it takes for your initial amount to be cut in half. And that's whatever we get here. That gives me about 16.27 as my value of t. By the way, since this is all in days per day, this would be 60.27 days. But okay with that one? Get in there. Doesn't matter how much you start with. To find the half-life, you just take your starting amount. Your ending amount is half of that. And then you solve that equation. Now, in our last part, it does give us a starting amount of 60. So it says if our starting amount is 60, how much is left after 50 days? Well, since our t is in days, all we have to do is replace t with 50. And obviously our starting amount, we make that 60. And this is something I type into my calculator. And that gives me about 33.76. This was in milligrams, so it would be milligrams of that isotope. Now, I want to point something out that is a little bit beyond the stuff that I'm asking or that I will ask for homework question or test question. But I just want to make a connection between this problem and the problems we were doing at the end of last class period, right? With the 1/2 as the base and 2 is the base. Does that make sense? So I'm going to make a connection there. And I'm going to do it based on what we found here. Okay. This is saying that it takes about 60.27 days for whatever substance to be cut in half. We had our equation as, just like over there, written as A equals P times e to the negative 0.0115 t. Last class period, we said if we know how long it takes to be cut in half, we could have used 1/2 to the t over the length of time it takes to get cut in half. And we just found that that was 60.27. Roughly. So the question is, are these two equations the same? Well, what I could do is just test something out. I could figure out what this number is. Take 1/2 to the 1 over 60.27 power. And then I could take this one and this we could rewrite as e to the negative 0.0115 all raised to the t power. So I could see if this number as my base is the same as that number as my base. And we'll type this into the calculator. No, do that. But or I'll type it into the calculator. So if I take 1/2 raised to the power 1 over 60.27, remember that's a rounded number, 60.27. I get that. If I took e to the negative 0.0115, sure enough, I get the same thing. Or at least it's close, it's very, very close because I rounded that to 2 decimal places up there. The 60.27 was rounded to 2 decimal places. So notice that these are essentially identical equations, just written different. Okay. So when we talked about our equations, which had base 2 and base 1/2 last time, those are written in a form where it's easy to see the length of time it takes to double or the length of time it takes to get cut in half. Whereas the other equation, this one, is written in a way where it's easy to see the rate of decay or the rate of growth. So this one's written in a way that it's easy to see the rate of decay or the rate of growth as a percent. This one's written in a way where it's easy to see the time it takes to double or get cut in half. So it's the same equation, just written in different ways. That's my point. Okay. Again, that's a little bit, I'm not going to ask you those things on a test. I'd ask you questions like these, but I'm not going to ask you to rewrite an equation in one way that we started in the original way. But it's nice to have both versions. Nice to have both versions because sometimes, like in example 4, you're given a decay rate. And then other times, like in example 2, we were given a time it takes to double. And in example 1, we were given a time it takes to be cut in half. All right. So it's easier to write one way or the other. Let's do another example. This one I'll do on the board because it's got a little bit of a trick to it. So, biologist records an estimated 450 bluegill in a pond 6 years after its construction. 5 years after that time, so 11 years after construction, he measures an estimated 1,400 bluegill in the pond. We're going to create an equation for the amount of bluegill in the pond T years after construction using continuous exponential growth. Okay, we're going to get the goal, and then we'll answer some questions after we get the actual equation. But getting the actual equation is the tricky part. So I'm going to assume continuous exponential growth. So it's going to be that A equals P times e to the RT power. That's the thing. It doesn't tell me how many bluegill are in the pond when it gets constructed, like at the initial time, right? So it says that 6 years after, there's going to be 450. That tells me that the amount that's in the pond six years after, so put a T as 6, is equal to 450. And we know that 1,400 is how many bluegill are in the pond 11 years after. And what I want to do is I'm going to take these two equations and use those to find my rate of growth and my initial amount. Okay. Anybody know how I do that in this case with an exponential, two exponential equations? We haven't done this yet, but what you would do is you would take one equation. I like using the one with the larger coefficient on the R. And since these two equations both have a P and an R, the way to solve them is to divide. Take 1,400 divided by 450. And set that equal to P times e to the 11R divided by P times e to the 6R. The reason why I like the larger exponent on top is because when I divide, these two p's will cancel out. And we can use our exponent rule, which is called the quotient rule of exponents, to make that right-hand side be e to the 5r. 11r minus 6r is 5r. And now we can solve this. Apply natural log to both sides. And then divide both sides by 5. And that's going to give me my rate. I'll round that to 4 decimal places here. So that's 0.2270. Is that right? Usually it's standard to round a rate or a proportion to 4 decimal places. That's the typical standard rounding for that. But if I give you this on a test, it'll specify what to round that to. Once we know the rate, now we can use either of these initial problems to solve for the starting amount. Okay. I'll use the second. I'll say 1400 was equal to P e to the 11 times 0.2270. This is just a number. So if I divide both sides by that number, I'll get my starting amount. I'll be okay with that. You could have also used the other equation, and if you use the other equation, you should get the same starting amount. I got an initial amount of about 115. Is that all right? And again, we'd specify what to round this to, whether to round this to the nearest whole number or to round it 2 decimal places. Those are the typical. Does that make sense? Let's say we were rounding the coefficient, the P, to a whole number and a rate to 4 decimal places. Then I know I have the equation A equals 115 times E raised to the 0.2270 times T as the equation that gives me the amount of bluegill in the pond T years after it was constructed.
Nitpick, but it'd be 115.27 rounded to the.
So this is where it gets a little bit weird. If you use this equation, it becomes 0.27, right? And if you use this equation, it becomes 0.26. But yes, you're right. If depending on which equation you use, this could be a 2.26 or a 0.27. Yeah, 6 or 7, depending on this equation, I got 0.26. The other equation, I got 0.27. That makes sense. Just has to. And again, the reason why they're just slightly different is because I rounded this R value. Okay. If I didn't round this R value, if I went out to like infinitely many decimals, then I'd be a little more accurate. And that's one of the reasons I use the whole number here rather than the rounded version. Okay, so there's the equation of bluegills in the pond 10 years after construction, assuming exponential growth. So how many bluegill were in the pond initially? We'd say about 115. And then if this pattern persists, how many years would it take to have 2,500 bluegills? That's the carrying capacity of the pond. At some point, can't have any more because there's just too many in the pond. So in that case, the second, I won't do that right now. You would just put the amount as 2,500 and solve it like we always do. Okay, the end amount as 2,500 and then solve it like we always do. So initial amount is 115. So 2,500 is equal to 115 times E to the 0.2270 T. Figure it out. Okay. Let's do another example. So we've done a lot with continual growth. Let's do an example where we're not compounding continually, but rather we're compounding monthly. So this says we invest money into a stock at 6% interest compounding monthly. Now it doesn't tell us how much money we do invest, so we'll just leave the initial principal as a P right now. Okay. So if our growth is at 6% compounding monthly, we have A equals T times 1 plus 0.06 over 12 raised to the 12T. Okay, that's our standard equation for compounding monthly. And then it asks, how long until my investment doubles? How long until my investment triples? I want you to try this on your own. Doubling would just be 2p on the one side. Tripling would just be 3p on the one side. Said they. Does that make sense? Base 12 minus natural. So that's apply natural log or apply log base. That makes sense. I use these to apply natural. And then you bring in 12t from the exponent alpha. All right, let's go through the steps for doing this. Some people are done, some people aren't, but that's all right. So the first thing I would do in an equation like this is I would divide both sides by p. Now, notice that that step becomes really uninteresting really quickly. So a lot of times I just start out with an equation that doesn't include the p in it, all right? So a lot of times I'll start out like this. So in other words, like if I ask how long until it triples, I'll just start out with the equation 3 is equal to 1 plus 0.06 over 12 raised to the 12t power. Okay. Tripling is like going from 1 to 3. So I don't have to even write a value for my starting amount other than just the implied 1. So I could have started that way here as well. Now I need to solve this equation. In order to solve this equation, well, there's a couple of different ways, but I could take log of this ugly number on both sides. You can rewrite that as 1.005 if you like, but log of this base. Or I could just apply natural log to both sides. That's what I did. I applied natural log to both sides, so I'll do it this way. And if I apply natural log of both sides, this exponent can come out front. And that'll give me a natural log of 2 is equal to 12 times t times the natural log of 1 plus 0.06 divided by 12. Okay. Usually what I do on my calculator is I'll take natural log of 2, I'll divide it by this number first, I'll hit enter, and then divide it by 12. But when I write it on the board, a lot of times I'll write it as dividing both sides by 12 times the natural log of 1 plus 0.06 over 12. So take natural log of 2 divided by 12, hit enter, then divide it by this other natural log. Or natural log of 2 divided by this natural log, hit enter, divide that whole thing by 12. That's what I typically do. Does that make sense? And when you do that, these are all just real numbers, and you'll end up with 11.58 roughly as the value of t. So at 6%, it takes about 11.58 years to double compounding monthly. So at 6% compounding monthly takes 11.58 years. Notice that works regardless of what my principal was. If I put in $1,000 and Warren Buffett puts in $10 million, his 10 million will turn into 20 million. At the same time, my 1,000 turns into 2,000. Okay. So this is regardless of the initial amount you put in. You do this one in the exact same way. We apply natural log to both. Actually, sorry. I did the natural log to both sides version in this one. So in this one, I'll do the log base, ugly base on this one. So I'll take log with base 1 plus 0.06 over 12. So that ugly base, and apply that to 3. is equal to log of that ugly base and apply that to the right-hand side. But log of this ugly base applied to the right-hand side just becomes a 12t. So here, all I would have to do is divide by 12. But I have to plug in that ugly base into my calculator. That's perfectly fine to do. Again, math, log base. So you can have log of that ugly base into your calculator with argument of 3. Hit enter, and then divide by 12. You should get 18.36. By the way, if you did this with taking natural log of both sides, it would be natural log of 3 divided by the natural log of that ugly base. Hit enter, divide that by 12. Notice you get the exact same number either way to do that. So whichever option you want, whichever version of solving you want is perfectly fine. So either apply natural log to both sides or apply log to this ugly base on both sides. Okay. I typically do the natural log thing just because I don't like using this as my base. But so in either case, you get about 18.36. 18.36 years to triple. In finance, the amount of time it takes for an investment to double, that's casually known as doubling time. So the time it takes to double is doubling time. That's something people talk about pretty regularly. Tripling time is not as common to talk about, but it's the same types of calculation. Now, I won't do this one. We could ask, for instance, if you start with 400, how long will it take to get to 2100? We've done stuff like that before. Same type of calculations. All right. Instead, I'll do the last one, which is example 7. In example 7, it says, assume you invest in a company and growth is compounding continually. What is the doubling time if the growth rate is 5%? This says compounding continually, so we'll go back to A equals P times e to the RT. And then what's the doubling time if the growth rate is 10%? So this is compounding continually. It's asking for the doubling time if the rate is 5%. I don't need to put P and 2P, I can just put 2 and 1, leave the 1 off. And this is the doubling time if the rate is 10%. So let's go ahead and solve these. These are pretty straightforward. Apply natural log. It's really nice to apply natural log to the right-hand side because natural log and e cancel each other out. So I'll end up with natural log of 2 is equal to 0.05 times t. Natural log of 2 is equal to 0.10 times t. By the way, what would it have ended up if the growth rate was 6%? Well, at this stage, it looked like natural log of 2 is equal to 0.06 times t, right? And if the growth rate were 12%, natural log of 2 is equal to 0.12 times t. So no matter what the percentage is, as long as it's continually compounded, this step would look the same. And then we just divide by whatever that rate is. So take natural log of 2 and divide it by 0.05 here on the left. That's a doubling time of 13.86 years. And over here, when I divide, it's 6.93. By the way, so here's why I'm bringing this up. First off, notice that the doubling time got cut in half as the rate doubled. Okay. That's the way it's always going to work. If we had a growth of 20%, because we be dividing by 0.2, then this number would have gotten cut in half. And we double in whatever half of 6.93 is. 4.4. 3.465, something like that. But my point is, the time it took to double gets cut in half. And that's a really, really big deal. If you think about doubling over 14 years versus doubling over 7 years, big difference. Now, the calculations with these are pretty straightforward, doubling times. There's actually a thing in finance called the rule of 70. That says the doubling time of an investment is approximately 70 divided by the rate of growth. I should say, let me rephrase that, the percentage of growth. So for instance, if we had a 5% growth, what we would say is that the doubling time is about 70 divided by 5. So 5%, 70 divided by 5. If I take 70 divided by 5, I get about 14. And if I had a 10% growth, the doubling time is about 70 divided by 10, which would obviously be 7. Pretty close to what our actual doubling time was. So why does the rule of 70 work? Well, the rule of 70 works because of the value of natural log of 2. All right. If you look at the value of natural log of 2, just type that in on your calculator. It's about 0.6931, et cetera, right? Which is kind of close to 7 if you move the decimal place over 2 spots. All right, so they round 69 to 70, and that's what it is. It's easier to remember a rule of 70 rather than a rule of 69. But technically, it's closer to 69 than it is to 7. But that's why the rule of 70 exists. This is like a shorthand rule for people who don't want to do the math. You know, the solving of an exponential equation. And they just want to have a really quick, approximation. So if you want a quick approximation, you could use the rule of 70 to figure out a doubling time. If you want more exact, then you solve that exponential equation. And again, it works because natural log of 2 is about 0.7. That's it. Over here, we're dividing by the rate as a decimal. Over here, we're dividing by the rate as a percent. So that's why the movement of 2 decimal spots over. Okay. But that's something that apparently people talk about. I'm not into finance, but a couple of my friends are, and they've said something about the rule of 70, and sure enough, when you look it up, it is there. It's an approximation technique. The more accurate is taking natural log of 2 and dividing it by your rate of growth. But if you want an okay approximate, take 70 divided by your percentage of growth. All right. Any questions about material from these applications? Let's see what we're trying to accomplish. Trying to set up one of these equations, something like A equals P times 1 plus R over M to the MT, or A equals P E to the R over E to the R times T, or P times 2 to the T over D power, or P times 1/2 to the T over D power. Setting up one of those equations and then using it, we can either solve for A by plugging in T, or solve for T by plugging in a value for A and solving via an exponential equation. All right. So that is it for chapter 4 of what we're going to cover.